the gastrointestinal tract.
It really is an incredible system.
When you look at the adult gut, this highly organized 9-meter-long factory of digestion and absorption, it's just astounding to realize it emerges from a process that is anything but simple.
Right. It's not a basic plumbing job.
Not at all. It's a high-stakes choreography. It involves cellular signaling, dramatic folding, extreme rotation, and specialized growth, all executed with, this impossible precision over a period of mere weeks.
And that choreography is the core of our deep dive today.
Yeah.
I mean, when you look at the final specialized product with its complex storage, mechanical mixing, all of its chemical processing, absorption capabilities, and then you add the integrated immune functions.
It's easy to forget where it all began.
Exactly. It's easy to forget that it all began as this simple single layer of endoderm, a flat sheet that then decided to roll up into a tube.
So our source material for today is... what are we looking
at highly detailed embryological text. It's essentially the definitive blueprint for the entire abdomen. Our mission is to extract the functional why and the developmental when behind this monumental effort.
Okay.
So we're focusing intensely on how 3 simple embryonic tissue layers, the endoderm, the mesoderm, and all the intervening molecular signaling factors, cooperate to form the entire GI tract, define the boundaries of the peritoneal cavity, and establish critical accessory organs like the liver and pancreas.
Okay, let's unpack this. We are charting the course of the gut, from a simple straight line to the complex, fixed, and folded system we carry within us. To truly appreciate the finished product, we have to start right at the foundation, establishing the primitive gut tube.
Right.
So how does a flat embryo develop a hole and then, wrap itself around a central digestive tube?
We have to begin with geometry. The primitive gut isn't a structure that just appears fully formed in the middle of the embryo. It's actually a necessary consequence of the embryo changing shape.
Changing shape from what to what?
From a flat disc to a 3-dimensional cylinder. It's derived entirely from the endoderm layer. During this process, we call embryonic folding. And this physical folding mechanism is what establishes the fundamental relationship between the central digestive system and the surrounding body wall.
And those folds are the key physical mechanism, right? We're talking about movement in 3 distinct dimensions, the cranial, the caudal, and then the 2 lateral folds all moving inward at the same time.
Yes, like the body is closing a zipper around its core.
That's a great visualization.
It is. You have the embryo initially just flat on the yolk sac. When the cranial fold occurs, the head region bends downward and forward, and that tucks the cranial endoderm underneath and initiates the foregut.
Okay, so that's the top end.
That's the top. Then the caudal fold happens. The tail region moves down and forward, tucking in the caudal endoderm, and that starts the hindgut.
And at the same time?
Simultaneously, the 2 lateral folds roll the sides of the embryo inward, bringing the 2 lateral edges together right at the midline.
So those lateral edges meet and then they fuse, which effectively encloses that endoderm layer within the structure of the torso.
Exactly. As those 3 folds bring the surrounding lateral plate mesoderm, we will definitely talk more about that shortly, together, they effectively close the embryonic body around the central, newly formed endodermal tube.
And that is the primitive gut.
That is the primitive gut. It runs continuously from the future head region to the future tail region. And this folding action, it not only forms the tube, but it also physically pinches off the gut from the large open space of the yolk sac.
Let's define its initial boundaries now, because those endpoints tell us where the system starts and where it finishes before, it opens up to the outside world.
Right, so the tube is initially sealed at both ends. Cranially, the gut terminates internally at what's called the buccopharyngeal membrane.
And that's?
That's this thin bilayer that marks the future site of the opening of the mouth and pharynx. And then caudally, it terminates at the cloacal membrane.
Which is the shared endpoint, right, for digestive and urogenital systems.
A temporary shared endpoint. Exactly. Everything between those 2 membranes is the primitive gut tube.
Okay, and we immediately divide that continuous tube into 3 specialized regions. How is that initial segmentation decided? What's the logic there?
Well, the initial segmentation is absolutely crucial for charting later organ development. Each segment gives rise to unique organs and, importantly, maintains distinct vascular supplies throughout life. So we start with the foregut, the midgut, and the hindgut.
Okay, let's define the limits. Where does the foregut end?
The foregut is the most cranial section. It gives rise to, everything from the pharynx down through the esophagus, stomach, liver, pancreas, and the proximal part of the duodenum.
And its boundary is really specific.
It's critical. It's defined as the approximate point where the liver's outgrowth, the common bile duct, will eventually attach. This corresponds roughly to the mid-duodenum in the adult.
Okay. And the defining feature of the midgut region, what makes it stand out?
The midgut is most easily identified during early development because it maintains a key temporary physical connection to the shrinking yolk sac.
Ah, through the vitelline duct.
Through the narrow duct known as the vitelline duct, exactly. This central portion of the tract will give rise to most of the small intestine, from the distal half of the duodenum all the way to the proximal two-thirds of the transverse colon. And this region is famous for its dramatic spatial relocation, which we will dedicate an entire section to later.
It's a huge topic.
Yeah.
And finally, the hindgut, which moves into that common terminal chamber before it separates.
Right. The hindgut forms the distal third of the transverse colon, the descending and sigmoid colon, the rectum, and the upper anal canal, and it terminates internally at the cloacal membrane.
So understanding these three basic regions, foregut, midgut, hindgut, is really the baseline for charting everything that comes next.
Everything.
Yeah.
The major rotations, the specialized organ budding, and the distinct vascular supplies that persist. You have the celiac artery for the foregut, the superior mesenteric artery for the midgut, and the inferior mesenteric artery for the hindgut. It's all set up right here.
So we have established that the endoderm provides the epithelial lining, that critical absorptive, secretory, and protective surface. But the GI tract is so much more than just a line tube. It has powerful muscles, highly complex vasculature, supportive connective tissue, and outer slippery serous layer. Where does all that robust supporting architecture come from?
This is the essential duality of gut development, the mesodermal partnership. While the endoderm forms the inner epithelial tube, the entire supporting structure arises from the surrounding tissue, the splanchnopleural mesenchyme.
Okay.
And this mesenchyme is itself derived from the lateral plate mesoderm that rolls up with the endoderm during folding.
Let's pause on that terminology, splanchnopleural mesenchyme. That's a very technical term. If the endoderm is the architect, drawing up the blueprints for the lining, what role does the splanchnopleural mesenchyme play? How can we think about it?
That mesenchyme is your construction crew, your general contractor, and your materials supplier, all rolled into one.
I like that.
It's the tissue that provides the strength, the movement, and the infrastructure. It differentiates into the connective tissue framework of the lamina propria and submucosa, the powerful inner circular and outer longitudinal muscular layers necessary for peristalsis.
And the blood supply.
The intricate network of blood vessels, the lymphatic drainage systems, and that outer protective and lubricating layer, the serosa.
That makes the dual origin incredibly clear. So you've got the endoderm defining the function, absorption, secretion, and the mesoderm defining the structure, movement, and supply. Strength, peristalsis, blood flow.
Exactly. This partnership is absolutely fundamental to every centimeter of the GI tract.
And you may put it differentiates into three major supporting layers.
Yes. To clarify that mesenchyme a bit further, you have the smooth muscle cells that make peristalsis possible, the lymphatic and blood vessels that fuel and sustain the tissue, and critically, the thin outer serous lining, which we call the visceral peritoneum, and that defines the organ's relationship with the abdominal cavity.
Moving beyond the basic structure now, let's look at the cellular destiny, specifically within that endodermal lining. We see this extraordinary event early on. The epithelium undergoes such rapid, intense proliferation that it literally causes a traffic jam and temporarily plugs the tube solid.
That temporary physiological occlusion is one of the most remarkable phenomena in this entire developmental process. It really is.
It seems so counterintuitive.
It does. The endodermal lining starts as a simple epithelium, but it rapidly grows, differentiating into stratified or hypersmatic cells. This rapid expansion, particularly noticeable in the esophagus and the entire duodenum, leads to the lumen becoming completely, if temporarily, occluded.
Wait, so if the whole point of a digestive tube is for passage, plugging it up seems like an evolutionary high-risk maneuver. What is the developmental rationale behind this necessary traffic jam?
It's believed that this aggressive proliferation is necessary to quickly expand the epithelial surface area and volume. The goal is to ensure the maximum number of specialized cells, villi, crypts, glands, are ready for function at birth, but as you pointed out, it's high risk.
Yeah.
If the lumen is occluded, it has to be cleared in a timely manner.
So how does the embryo clear this plug and reestablish patency? What's the mechanism?
The process relies on precisely controlled tissue destruction and merging, which we call recanalization.
Yeah.
This happens primarily via apoptosis-programmed cell death of the central epithelial mass.
And there's another part to it.
Yes, combined with the formation of numerous vacuoles or fluid-filled pockets within the surviving cells. These vacuoles then coalesce or merge together, effectively dissolving the cell mass and reestablishing a single continuous patent channel.
And the failure of that apoptotic mechanism has direct, severe clinical consequences.
It absolutely does. Failure of this process, particularly in the duodenum and later in the biliary ducts, leads directly to structural blockages known as atresia, which is a complete blockage, or stenosis, which is a narrowing. The window for successful recanalization is critical, typically closing between weeks 8 and 10 of gestation.
Here's where it gets really interesting for me. The molecular control that orchestrates this entire process, telling cells what to be, when to proliferate, and when to undergo apoptosis. What are the major chemical signals driving this incredibly precise patterning?
The orchestration relies on a continuous, highly localized chemical conversation between the endoderm and the surrounding mesenchyme. And the key player in early gut patterning, a true master regulator, is the molecule sonic hedgehog.
Shh.
Huh.
It sounds like a whimsical name for something so fundamentally important. What exactly is its job here?
Shh. Is secreted by the endoderm itself, and it acts as a morphogen signal to the surrounding mesenchyme.
A morphogen, so it creates a pattern.
Yes, a morphogen is a signaling molecule that diffuses out from a source and forms a concentration gradient. So you get a high concentration near the endoderm and a lower concentration further away. This gradient instructs the mesenchyme on how to differentiate.
So the concentration of Schur literally determines the mesenchyme's destiny.
Precisely. For example, high concentrations of SHASH near the epithelial surface might inhibit the formation of outer muscle layers while promoting the inner ones. So it's defining the thickness, the type, and even the eventual location of the muscular layers of the gut tube. This chemical gradient determines the mechanical properties of the entire tract regionally. It's the blueprint being executed in real time.
Are there other regional signals involved beyond Sch, which seems to cover the bulk of the gut? Or is it the only player?
Oh, absolutely, there are others. While SHU sets the broad pattern, specific regional differentiation relies on unique local transcription factors. The text highlights the development along the cranial-caudal axis, determining, say, that this bit becomes pancreas and that bit becomes small intestine, is controlled by homeobox genes and other transcription factors.
Can you give us a specific example of one of these regional determinants, something that's really targeted?
Certainly. Factors like TBX4 are crucial for defining the region where the respiratory diverticulum buds off the foregut. But even more relevant to the gut itself is PDX1, which stands for pancreatic and duodenal homeobox 1.
PDX1.
PDX1 is essential in defining the endoderm's fate in the duodenal region and is the key regulator ensuring the development of the pancreas. So these transcription factors ensure that the correct anatomical structure develops in the correct location along the cranial-caudal axis, adhering strictly to the plan.
That makes the developmental program seem incredibly robust.
It's amazing. Now let's solidify our understanding of the outer layer before we move down the tube. We mentioned the serous lining, the visceral peritoneum, which is vital for structure, suspension, and frictionless movement.
That lining is the splangnopleric mesenchyme's second critical derivative. It forms the boundary between the organ and the abdominal cavity. And this outermost layer, the serous lining of the gut, known as the visceral peritoneum, is composed of specialized surface cells called mesothelium.
What's special about the mesothelium? It sounds like simple, flat tissue, but you mentioned it has microvilli. Why would a smooth lining need microvilli?
It is not simple at all. I mean, they're flat cells, which gives that smooth, slick surface we see, but they possess abundant microvilli on their free surfaces, and they are highly metabolically active.
What are they doing? This microvilli-covered surface aids in the production of the lubricating peritoneal fluid, and, importantly, they possess transport capability. They actively move fluids, electrolytes, and immune cells across the surface. This thin layer is essential for preventing friction between moving organs and for the formation and organization of the mesenteries, which we will analyze in depth later.
Okay.
This first section has given us the fundamental building blocks. We have the endoderm tube, the mesodermal support crew, the molecular operating system, and the crucial boundary layer. That sets the stage beautifully. Let's move sequentially down the gut tube, starting with the most proximal section, the four gut derivatives. Starting with the esophagus and the stomach. Exactly, which introduced this whole concept of extreme spatial movement.
Right.
Starting right after the pharynx, we have the esophagus. And this structure's initial challenge is just sheer length. It has to elongate dramatically to bridge the rapidly increasing distance between the growing head and pharynx and the stomach and the upper abdomen.
Yeah.
Rapid growth is an understatement. The esophagus begins its significant lengthening around stage 13, which is roughly 3 to 5 weeks of development. It needs to elongate incredibly fast to keep pace with the massive expansion of the neck and the developing thorax.
And if this elongation process is compromised,
The result can be severe.
what kind of issues arise from failed elongation?
Well, the most serious defects result in esophageal atresia, where the esophagus ends in a blind pouch and often has a communication of fistula with the trachea. This is often linked to errors during the separation of the respiratory tract from the foregut.
And other issues.
Failure of elongation or failure of the muscle layers to function correctly can also contribute to conditions like congenital hiatal hernia, though the atresia is the more immediate and life-threatening issue.
And the epithelial lining within the esophagus undergoes a fascinating transformation that prepares it for its adult job of high-speed transport and protection.
It definitely shifts its identity. Initially, the endodermal lining of the primitive esophagus is composed of ciliated epithelium.
So like tiny hairs sweeping fluid along.
Exactly, which is useful in the early embryonic context. However, as the fetus matures and prepares for swallowing food, this lining must change to resist abrasion.
So what's the timeline for that shift to the adult lining? When does it get tough?
The change begins with stratification. The epithelial cells begin stacking up in layers, and this process generally happens around the second trimester. It eventually results in the tough, protective, stratified squamous epithelium we see in the adult. And this lining is designed specifically for protection against mechanical stress and the caustic nature of reflux stomach contents.
Now let's discuss the unique muscle structure. The esophagus is the only part of the digestive tract that has a dual muscular origin, which means we have voluntary control over the initial phase of swallowing. That's not true anywhere else in the gut.
This is a key anatomical distinction and one of the clearest examples of how distinct embryological origins define adult function. The muscular layers surrounding the esophagus are split. The upper third of the esophagus develops striated muscle, the type of muscle we consciously control. And critically, this tissue is not derived from the standard splenopleural mesenchyme.
Where does it come from?
It comes from the mesenchyme of the pharyngeal arches. And then, the lower two-thirds develop standard smooth, muscle-involuntary muscle derived from the splenopleural mesenchyme surrounding the gut tube.
That's a fantastic linkage. So the origin from the pharyngeal arches, which also give rise to the muscles of the head and neck, that explains why the start of the swallow is voluntary.
Precise.
And then the standard gut mesenchyme takes over for the involuntary peristaltic waves.
Exactly. The central nervous system initiates the voluntary swallow using the arch-derived muscles, and then the intrinsic system of the gut, the smooth muscle derived from the body cavity mesenchyme, takes over to complete the involuntary transit into the stomach.
And this functional split and maturation timeline links to a very common phenomenon in newborns: reflux. You mentioned the late development of the cardiac sphincter.
Yes, that late maturation is a crucial clinical takeaway. The functional integrity of the junction between the esophagus and the stomach is governed by the cardiac sphincter, or lower esophageal sphincter. And this structure is one of the last to develop and mature. It often doesn't reach full functional capacity until late gestation or even into the third trimester.
So parents dealing with a fussy 4-week-old aren't necessarily dealing with a defect. They're dealing with a standard, albeit inconvenient, developmental timeline.
Precisely. This structural and functional immaturity is the reason physiological gastroesophageal reflux is incredibly common in neonates. The immaturity causes transient relaxations of the sphincter, leading to frequent regurgitation. It typically peaks around 4 to 6 weeks postnatally as the digestive volume increases.
And it goes away on its own.
It is generally self-resolving as the sphincter tone matures.
Okay, let's move down to the main mixing chamber, the stomach. This organ undergoes the most dramatic spatial realignment of the entire gut, which you described as a complex choreographed dance. We need to visualize this movement.
The stomach is initially visible quite early, around stage 13. It's just a fusiform, spindle-shaped dilation of the foregut tube, and it's suspended in the peritoneal cavity by its mesenteries.
And it has 2 attachments, right?
Crucially, yes. It starts with both a dorsal attachment, the dorsal mesogastrium connecting it to the posterior body wall, and a ventral attachment, the ventral mesogastrium connecting it to the septum transversum, which is where the liver is.
And the stomach doesn't stay straight. It has to rotate along 2 axes. Let's tackle the first step, the 90-degree rotation along its long axis. How can we visualize that movement?
Okay, imagine the stomach as a thick vertical sausage. If you're looking down at it from the head, so a cranial view, The entire structure rotates 90 degrees clockwise. Clockwise. You can think of it like taking a book that is standing up and turning it 90 degrees on a shelf. This single movement defines the basic curvature.
What happens to the original anterior, posterior, left and right walls during this 90-degree twist?
The rotation repositions everything. The original left surface now faces anteriorly, so it's the front. The original right surface now faces posteriorly, it's the back. And the dorsal border, which grows much faster than the ventral border.
Because of that differential signaling we talked about.
Exactly. Because of that, it gets pulled to the left side and becomes the greater curvature. Meanwhile, the slower-growing ventral border moves to the right and becomes the lesser curvature.
That 90-degree clockwise turn establishes the structure, but then there's a second rotation, an anteroposterior tilt, that gets it into its final oblique resting position.
Correct. The second rotation occurs along the anteroposterior, or front-to-back, axis, and this results in a crucial tilting motion. The pyloric region, that's the caudal end where the stomach meets the duodenum, shifts to the right and moves cranially, or upward.
And the top part.
Conversely, the fundic region, the cranial dome-like end, shifts to the left and moves caudally or downward.
What is the main lasting anatomical consequence of these two rotational movements working in concert? What's the big picture outcome?
The rotations achieve several profound things that shape the adult abdomen. First, they establish the stomach's final oblique position, tucked high in the upper left quadrant. Second, and critically, they physically pull the duodenum into its characteristic C shape.
Which is necessary for the pancreas.
Absolutely necessary for cradling the developing pancreas.
And the third major consequence is the creation of a brand new space.
Yes, the rotation pulls the original dorsal mesogastrium over to the left and backward, initiating the formation of the omental bursa, often called the lesser sac. This is the deep peritoneal space situated directly posterior to the stomach and anterior to the pancreas and left kidney. This space only exists because of the stomach's rotational path.
The stomach is an engineering marvel that moves into position and then slowly builds up its functional strength. Let's look at the timeline for when the stomach actually starts functioning as a chemical processor.
Well, the mucosa development is sequential. It lags behind the structural positioning. The key secretory cells, parietal cells, which produce acid and intrinsic factor, and chief cells, which produce pepsinogen, can be morphologically identified relatively early, around 9 to 11 weeks.
But seeing them doesn't mean they're working.
No. Functional acid secretion is significantly delayed.
When does that chemical factory really switch on?
Acid secretion is measurable only after 14 weeks, and the significant increase in acid production, vital for sterilization and initial digestion, occurs later, between 19 and 20 months. Full functional acid capacity is truly a late-stage development, right before birth.
And this late development has immediate consequences for the newborn, especially those born prematurely or under stress.
This is a great clinical comparison point. The stomach of a term neonate is quite acidic. Gastric acid levels are typically 2 to 3 times higher than those measured in the maternal serum.
Why so high?
These high acid levels are functionally important. They're thought to aid in the absorption of certain minerals like iron and calcium and provide a necessary barrier against pathogens.
But if they are born early?
In contrast, preterm neonates often have much lower acid levels due to this delayed maturation. And this difference is clinically relevant. The term infant needs that acid for absorption. But a stressed infant, especially if premature, is susceptible to potential ulcer formation if the mucosal barrier is stressed or immature. The balance between acid production and mucosal protection is fine-tuned right up until delivery.
Finally, the muscle layers. We know the stomach requires strong multidirectional churning power. We have the standard longitudinal and circular layers, but also an oblique layer. When does that oblique muscle, crucial for powerful mixing, finally develop?
It is the last of the 3 muscular layers derived from the splenopleurocoelic mesenchyme. The oblique muscle layer, which is essential for the powerful multidirectional churning action of the stomach, doesn't appear until relatively late, around post-fertilization week 16.
So again, form first, then function.
Exactly. This reinforces that the morphological form is established first by rotation, and then the mechanical functional capacity is built up incrementally in the second trimester.
A structure that rotates itself into position and then slowly builds its muscular and chemical strength. Let's shift our focus now to the critical accessory organs, the liver, the pancreas, that bud directly off the foregut, starting with the fixed crossroads of the entire system. the duodenum.
The duodenum is a complex organ because it represents the critical pivot point, straddling the original foregut-midgut boundary. It acts as the fixed gateway through which all digestive contents must pass and where the major accessory organs, the liver and pancreas, dump their output.
So it has a necessary split origin. Where is the exact embryological dividing line?
The duodenum is derived from the caudal part of the foregut and the cranial part of the midgut. The exact defining line for this embryological division is the entrance point of the common bile duct. Everything proximal, so closer to the stomach, is foregut-derived, and everything distal, closer to the jejunum, is midgut-derived. And this split explains the complexity of its blood supply. It receives input from both the celiac and the superior mesenteric arteries.
We mentioned rotation earlier, but the stomach's massive movement has a secondary, profound, and permanent impact on the duodenum's location.
It is entirely a consequence of the stomach's twist. The stomach's 90-degree and subsequent tilting rotations force the duodenum into its characteristic C shape. And this C loop is essential because it must wrap around the developing pancreas, cradling it in place.
But the lasting impact is fixation.
It is. The duodenum begins development suspended by its dorsal mesentery, just like the stomach. Following the stomach's rotation and the duodenum's repositioning against the posterior abdominal wall, its dorsal mesentery fuses completely with the posterior parietal peritoneum. This process is called retroperitonealization.
And the effect is stability.
Absolute stability. Because of this fusion and the subsequent resorption of that fused mesentery layer, the majority of the duodenum, specifically the second, third, and fourth parts, along with the pancreas nestled within its curve, becomes secondary retroperitoneal.
So it's locked down.
It is fixed securely to the posterior body wall, allowing it to serve as this stable gateway for critical enzyme delivery.
Let's quickly circle back to the high-stakes proliferation issue we discussed in Section 1, because the duodenum is the most vulnerable point for the resulting clinical problems.
It is the classic hotspot for this phenomenon. The temporary, intense epithelial proliferation that occurs around stages 13-14 often completely occludes the duodenal lumen. The timing of successful recanalization via apoptosis and vacuolization is absolutely critical, and it takes place typically between weeks 8 and 10.
So the period between 8 and 10 weeks is the duoden die time for the duodenal lumen. If that process stalls, what is the consequence for the neonate?
Failure to establish a patent lumen in the duodenum leads directly to duodenal atresia, which is a total blind end, or stenosis, a severe narrowing.
And that would present immediately at birth.
Immediately. Since the duodenum is the first major intestinal segment, obstruction here causes severe vomiting, often bile-stained, in the newborn, and necessitates urgent surgical intervention to bypass the blockage.
Now for the pancreas. This organ is truly remarkable because it forms through the perfect fusion of two separate entities that start on opposite sides of the tube.
The pancreas originates from two separate endodermal outgrowths, or buds, that emerge from the duodenal wall right near where the bile duct is developing. And this dual origin is the central key to understanding its complex anatomy.
Let's define the two buds and their future components in detail. What are they?
First, we have the ventral bud. This bud appears earlier, around stage 11, and is initially located ventrally, in front of the gut tube, intimately associated with the growing common bile duct.
And what does the smaller bud become?
This smaller bud will eventually swing around to form the inferior part of the head of the pancreas, and critically, the entire main pancreatic duct, also known as Wirsung's duct.
And the second, larger bud?
That is the dorsal bud, appearing slightly later, around stage 13. It is much larger and forms the superior part of the head, the entire body, and the tail of the pancreas. It also gives rise to the initial duct system, which often persists as the accessory duct, or Santorini's duct.
So how do these two separate, spatially distinct buds end up fusing into one cohesive organ that lies horizontally behind the stomach? We need a mental image of that transformation.
This is a structural miracle driven entirely by the stomach and duodenum's movement. As the duodenum rotates into its C shape, remember, it's being pulled by the stomach, it acts like a hinge.
A hinge?
Yes. The ventral bud is carried along the lateral wall of the duodenum and moves dorsally, swinging behind the duodenum to meet and fuse with the large dorsal bud.
That's a huge movement. When is this fusion completed?
The fusion process is highly reliable and is completed relatively quickly by stage 16, which is around 7 weeks of development. The subsequent duct systems then merge and reorganize. The duct from the dorsal bud typically fuses with the ventral duct system, creating the unified adult main pancreatic duct.
This means the complex 3D architecture and even the duct drainage pattern of the pancreas is purely a consequence of the stomach's earlier rotation.
Absolutely. The final complex shape, the head cradled in the C-loop, the body extending across the midline, the tail reaching the spleen, is all dictated by that 90-degree twist the stomach performed weeks earlier.
Speaking of fusion issues, let's discuss the specific, often obstructive, clinical anomaly that occurs when the ventral bud doesn't complete this precise migratory path.
That is the famous annular pancreas. This specific and potentially dangerous defect occurs when the ventral pancreatic bud, instead of migrating cleanly in one piece, splits into two parts.
Oh.
These two parts then migrate in opposite directions, one superiorly, one inferiorly, and completely encircle the developing duodenum before fusing dorsally.
So the pancreatic tissue effectively forms a tight, fibrous ring or collar around the duodenum.
Precisely. The consequence is a fibrous ring of functional pancreatic tissue that completely or partially constricts the duodenum, leading to high-level duodenal obstruction. And this often presents clinically with symptoms similar to duodenal atresia.
Before we move on to the liver, let's quickly discuss the development of the pancreas's specialized endocrine function, the insulin and glucagon factory.
Right, the endocrine cells, which coalesce into the islets of Langerhans, differentiate relatively early. They're identifiable by stage 14. Hormone production begins quickly thereafter.
How quickly?
We see measurable expression of insulin and glucagon by 9 weeks of gestation. Functionality rapidly increases, ensuring the fetus can manage its own glucose metabolism soon after.
And you mentioned a key transcription factor driving this specific cellular identity.
Yes, the transcription factor PDX1 is paramount. It is the molecular switch required for the pancreatic endoderm to commit to its specific fate, dictating not only the structure, but also the ability to produce these essential hormones. Its role underscores how early molecular cues define the functional capacity of the mature organ.
Moving on to the liver, the organ that demands attention simply because of its massive size and crucial early functional importance.
The liver starts as the hepatic diverticulum, an endodermal outgrowth that rapidly invades the dense, highly specialized mesenchyme of the septum transversum. This mesenchyme is the crucial non-endodermal partner. It acts as the template, yielding the connective tissue framework, the capsule, the portal tracts, and critically, the initial hematopoietic cells that populate the liver.
The size differential is staggering. Why does the liver need to be so disproportionately large in the fetus?
It is truly enormous. By 10 weeks, the liver can constitute up to 10% of the total body weight of the embryo.
10%.
10% is far larger than its adult ratio.
Yeah.
And this massive size is an absolute necessity because of its critical, non-digestive early functions, primarily blood production and early metabolism.
What are those primary roles that necessitate such a huge organ?
Its main initial roles are hematological and metabolic. It becomes the major site for hematopoiesis, the formation of all blood cells, starting around week 6. This function is paramount throughout the second trimester before production primarily shifts to the bone marrow near birth.
And metabolically?
Metabolically, it is heavily engaged in handling the fetus's nutrient supply, particularly rapid fatty acid synthesis, and the storage and release of glucose and glycogen.
And we noted earlier that fetal growth restriction often targets the liver.
Precisely. If a fetus experiences growth restriction due to placental issues, the liver is often disproportionately small because the blood flow is shunted away from the portal system towards the brain, prioritizing neurological development over accessory organ growth. This confirms its status as a high-demand, high-growth, but ultimately dispensable organ in crisis.
Finally, the biliary system, which stems from the caudal part of that initial hepatic outgrowth.
Yes, the hepatic diverticulum divides. The cranial part forms the liver cells, and the caudal part forms the duct system. And the caudal part specifically forms the gallbladder and the cystic duct.
And just like the duodenum and the esophagus,
It's subject to the same proliferation issue.
meaning they too must recanalize.
Yes. The epithelial proliferation is so intense that the duct systems often become temporarily solid cords of cells. They must undergo recanalization via apoptosis. The source material notes that these ducts are typically patent, or open by a later timeline, between weeks 16 and 20.
And failure of this process.
Failure of this recanalization process, particularly in the larger extrahepatic ducts, leads to extrahepatic biliary atresia, EBA.
Which is a severe, time-sensitive neonatal condition.
EBA is life-threatening. If the bile ducts are blocked, bile cannot drain from the liver. This leads to rapidly progressing jaundice, liver failure, and cirrhosis within months of birth. It requires prompt surgical intervention, often involving a Kasai procedure, to establish bile drainage. This really highlights how critical timely apoptosis is.
The foregut alone is a story of dual origin, rotation, fusion, and recanalization failure, leading to some of the most profound congenital anomalies. Now we enter the midsection, where the choreography involves not just a twist, but a spectacular temporary eviction. We're talking about the midgut.
The midgut loop is where the body deals with a critical real estate crisis. The source material refers to this developmental phase as the spectacular, controlled anatomical repositioning of the intestinal coils, and it is arguably the most complex mechanical operation of the entire tract.
So why does the midgut need to perform this radical maneuver of growth and rotation? What's driving it?
It's a space issue, driven by differential growths. The endodermal tube and the surrounding mesenchyme of the midgut elongate incredibly rapidly to maximize surface area. This rapid growth forms the primary intestinal loop, and this loop is suspended by a narrow dorsal mesentery and uses the superior mesenteric artery, SMA, as its rigid central anatomical axis of rotation.
And what are the physical constraints that necessitate the next step? Why can't it just stay inside?
The abdominal cavity, which is bound by the body wall, is simply too small to contain the rapidly growing intestinal loop and the massive foregut derivatives we just discussed. Specifically, the two major organs expanding at an astronomical rate, the large hematopoietic liver and the enormous temporary embryonic mesonephros, the primitive kidneys, they occupy all the available space.
This overcrowding triggers the famous event, the physiological herniation?
Yes, the great eruption. The midgut is physically forced out of the abdominal cavity starting late in stage 14, which is around the 6th week. It herniates into the open space of the umbilical colilome, which is the cavity contained within the umbilical cord itself.
And this is normal?
This is a normal, necessary, and temporary event.
So the intestines spend a period of time, approximately 4 weeks, outside the body cavity, just hanging in the umbilical cord. While they're out there, the first structural movement occurs.
Correct. While herniated, the first major rotational event takes place. The entire midgut loop rotates 90 degrees counterclockwise around the fixed axis of the superior mesenteric artery.
Let's visualize that 90-degree twist. We have the loop anchored by the SMA. How does this initial rotation position the two limbs?
The midgut loop has a cranial limb, which becomes the future small intestine, the jejunum, and a caudal limb, which becomes the future ileum and colon. That initial 90-degree counterclockwise rotation causes the cranial limb to move to the right and the caudal limb to move to the left.
Okay.
And this sets the perfect initial geometry for the subsequent retraction sequence.
If the 6th week is the eruption, when do the intestines return, and what is the signal that triggers that retraction process?
The environment changes. The liver begins to regress in size relative to the rest of the body, the mesonephros degenerates, and the abdominal cavity itself rapidly expands and matures. This expansion relieves the pressure, and the intestine is triggered to return. And that retraction process begins around the 10th week, or stage 23.
Is the retraction chaotic, or is there an orderly sequence we need to follow?
The sequence is highly precise, and it dictates the entire final spatial arrangement. If the return is not sequential, we get catastrophe.
What returns first?
The cranial limb, the future small intestine, the jejunum and ileum returns first. Because it rotated 90 degrees previously, it enters the abdomen and immediately takes up position on the left side, pushing the small bowel centrally.
That sounds like a rope being spooled back into a barrel where the first rope in gets tucked neatly in the center.
Exactly. The central and left regions are quickly filled by the small intestine. This means the caudal limb, which holds the future colon components, must return last. As it retracts, it is forced against the right side of the abdominal cavity.
And that final retraction forces the completion of the major twist.
Yes. As the caudal limb pulls back, the entire loop rotates an additional 180 degrees counterclockwise.
So 90 plus 180.
When we add this 180 degrees to the initial 90 degrees that occurred during herniation, we complete the defining movement of the midgut, a total rotation of 270 degrees counterclockwise around the axis of the superior mesenteric artery.
The 270-degree twist is truly the defining structural feature of the abdomen. What is the final resulting configuration established by this complex three-part sequence?
The rotation and retraction sequence positions every segment. The small intestine, having returned first, fills the center and left abdomen. The large intestine ascending, transverse, descending colon comes to frame the periphery of the cavity. And crucially, the caecum, which forms as a ventral enlargement of the caudal limb, descends from its initial position right under the liver,
The subhepatic position.
the subhepatic position, into its final adult location in the right iliac fossa.
This sounds like a high-precision manufacturing line, where one misstep or incomplete rotation leads to life-threatening issues in the newborn.
Failures in this precise choreography, often summarized as malrotation or non-rotation, are indeed severe. If the 270-degree twist is incomplete or entirely absent, the consequences are disastrous because the intestines are improperly fixed.
If they are improperly fixed, what does that look like anatomically, and why is it so dangerous?
Instead of having a broad attachment base of the small bowel mesentery running obliquely from the upper left to the lower right abdomen, the entire small intestine is left hanging precariously on a very short, narrow mesenteric base directly over the SMA.
The structural failure risk, then, is twisting?
Precisely. The primary life-threatening risk is intestinal volvulus, the twisting of the bowel around the narrow axis of the superior mesenteric artery. Volvulus cuts off the arterial blood supply to the entire midgut, leading to a rapid catastrophic intestinal ischemia and tissue death.
So it's a surgical emergency?
Malrotation must be recognized and surgically corrected immediately in infancy to tack down the intestines and widen the mesenteric base.
Before we leave the midgut, let's mention the most common congenital anomaly of this region, which relates back to that necessary but temporary connection to the yolk sac.
That is Meckel's diverticulum. It results from the incomplete obliteration and persistence of the vitelline duct, the temporary stalk connecting the midgut loop to the yolk sac. Instead of fully disappearing, a small portion remains as a true diverticulum, typically located on the anticenteric border of the ileum, about 60 centimeters proximal to the ileocecal valve.
And sometimes this diverticulum contains tissue that shouldn't be there.
Yes, often containing ectopic gastric or pancreatic mucosa, which can cause bleeding or inflammation and is often confused clinically with appendicitis. Its persistence is a stark reminder of the gut's temporary external connection during the herniation phase.
Let's discuss the internal architecture, the maturation and micropatterning of the epithelial surface that finally becomes ready for absorption.
The structural growth is remarkable. By birth, the small intestine is proportionally long, roughly 30 to 50 centimeters in length, maintaining the correct ratio to body length. But the surface structure is key. The intestinal lining must maximize the surface area for absorption.
And that complex architecture, the villi and the crypts, is completed prenatally. Is it ready to go at birth?
Yes, the specialized surface topography, which involves the establishment of the central villi, the absorbing projections in the surrounding crypts, the areas of stem cell renewal and secretion. This whole process, known as radial patterning, is completed before birth. This ensures that the epithelial lining is fully differentiated and capable of nutrient absorption the moment the infant begins feeding postnatally.
Amazing.
This readiness is a testament to the precision of the developmental timeline.
That is a fascinating transition from an empty, fluid-filled tube hanging outside the body to a fully functional, specialized absorptive system in just a few months. We've covered the foregut and the midgut. Now we move to the final terminal section where separation is the primary goal, the hindgut.
The hindgut is responsible for completing the large intestine, forming the rectum, and most critically, executing the highly sensitive and necessary process of separating the digestive tract from the urogenital tract.
Let's start with the parts of the colon derived from this section, completing the frame of the abdomen.
The hindgut forms the distal third of the transverse colon, joining the midgut derivative, the entire descending colon, the sigmoid colon, the rectum, and the upper part of the anal canal. Once these segments are in place, they finalize the large intestinal frame around the small intestine.
How does the appendix form, and why do surgeons often note that its location is so variable in adults? Sometimes retrocecal, sometimes pelvic.
Well, the cecum itself, where the appendix attaches, begins as a simple ventral enlargement of the caudal midgut limb, appearing around stage 15. The appendix then develops as a secondary, narrow diverticulum from the tip of the cecum. Initially, it sits right at the very end.
So why does it move?
The appendix doesn't move so much as the cecum grows around it. As the walls of the cecum expand disproportionately after birth, particularly the lateral wall, the appendix's base shifts its relative position. This differential growth is what leads to the wide variety of adult positions, retrocecal, pelvic, posteal, and so on.
What about the functional maturation of the large intestine? When is it ready for its postnatal job of hydration control?
The large intestine matures relatively early, with its fundamental structure in place by about 14 weeks. Its epithelial lining must quickly develop the specialized capacity for water and electrolyte absorption, which is its primary postnatal function. essential for stool formation and overall hydration management of the infant.
Now for the highest stakes developmental event of the hindgut, the division of the temporary common chamber into two separate exits.
That common chamber is the cloaca. It serves as a temporary shared termination point for both the primitive gut tube, the rectum, and the primitive urogenital tract, the urogenital sinus, and it's sealed externally by the cloacal membrane.
And the division itself relies on a mesodermal structure growing down like a partition wall.
That partition is the urorectal septum. It's a wedge of mesoderm that begins growing caudally, or downward, from the angle between the allantois, which is the primitive bladder, and the hindgut. This septum acts like a dividing wall, progressively separating the cloaca into two tubes.
Okay, what are the two tubes?
The primitive rectum and anal canal, which remains dorsal in the back, and the urogenital sinus, which becomes ventral in the front.
When does this separation occur, and what is the time frame for success?
This separation is a swift, critical event happening between stages 13 and 17. The septum must successfully fuse with the cloacal membrane, dividing it into the dorsal anal membrane and the ventral urogenital membrane.
And the inevitable failure scenario, what happens if it doesn't fuse correctly?
Failure of the urorectal septum to fully descend or properly fuse results in various forms of persistent cloaca or anorectal fistulas. This means there is still an abnormal communication between the digestive tract and the urogenital tract, the vagina, bladder, or urethra, which must be corrected surgically to prevent chronic infection and malfunction.
The final structure in the line is the anal canal, which uniquely exhibits a clear, permanent, dual embryological origin in the adult anatomy. This explains things like the differences between external and internal hemorrhoids, for example.
This is a fundamental anatomical concept that dictates surgical practice. The anal canal has two distinct origins. The upper part is derived from the endoderm of the hindgut,
Okay.
and the lower part is derived from the ectoderm, which forms an external depression that invaginates inward, called the proctodeum or anal pit.
And there is a visible line that marks this precise junction in the adult body.
That is the pectinate line. This line is the remnant of the historical location where the thin anal membrane, the lower part of the cloacal membrane, ruptured. The rupture of this membrane happens around stage 18, connecting the endodermal gut lumen to the outside world for the first time.
Why does this dual origin matter so profoundly in adult physiology and surgery?
The dual origin dictates every sensory, vascular, and neurological difference above and below that line. The upper endodermal part receives autonomic innervation, so it's involuntary and insensitive to pain.
Right.
It gets its blood supply via the inferior mesenteric system and drainage to the portal venous system. The lower ectodermal part receives somatic innervation, which means voluntary control, and it's highly sensitive to touch and pain. It has a different vascular supply and drains to the caval system. This knowledge is crucial for diagnosing and treating painful lesions versus non-painful ones in that region.
Finally, what is the most common anomaly related to this terminal separation and membrane rupture?
Imperforate anus is the most frequent anorectal anomaly. It stems from the failure of the anal membrane to degenerate and rupture at stage 18, or from severe, high issues with the urorectal septum division. This leads to a blind-ending rectum or atresia, or the development of abnormal fistulous tracts communicating with the urethra or bladder.
We have successfully charted the development and rotation of the entire 9-meter GI tract, but none of this structure exists in isolation. It requires a specialized support system, the peritoneal cavity and its attachments, to hold everything in place, allow for movement, and define organ location.
This final section explains the structural engineering behind the digestive tract. It details why certain organs, the stomach, the small intestine, are free-moving, while others, the pancreas, the duodenum, are firmly fixed. And it all comes down to the development of the peritoneal cavity and the fate of the mesenteries.
Let's define the cavity itself, which is the space within which all this movement occurs.
The peritoneal cavity originates from the portion of the intraembryonic celum that remains after the lateral folding is complete. It's lined by two parts of the peritoneum. You have the parietal peritoneum lining the body wall, which is derived from somatopleuric mesenchyme, and the visceral peritoneum lining the organs, which is from the splenopleurotic mesenchyme.
And the cavity is the space between them.
The cavity is the potential space between these two layers, filled with lubricating fluid.
And the mesenteries are simply the double-layered sheets of visceral peritoneum that connect the gut tube to the body walls, carrying the critical nerves and blood vessels.
Correct. And we must distinguish between the two primary attachments. The dorsal mesentery is the massive, ubiquitous structure. It suspends the entire foregut, midgut, and hindgut to the posterior abdominal wall. It is the primary site involved in all the rotation, elongation, and subsequent fixation events we have discussed.
So it's the main player?
It is. Its complex folds become the various adult mesenteries, the mesentery proper, transverse and mesocolon, sigmoid mesocolon.
And the ventral mesentery is far more restricted spatially.
The ventral mesentery is confined only to the foregut region, so the lower esophagus, stomach, and the superior part of the duodenum. Its existence in this region is due to the liver growing directly into the septum transversum, which is attached ventrally. The liver physically splits this ventral attachment.
What are the two key ligaments derived from that ventral mesentery after the liver has split it?
The ventral mesentery is divided by the liver into two parts. Dorsal to the liver, it forms the lesser omentum, which connects the liver to the stomach in duodenum and contains the crucial portal triad. And then ventral to the liver, it forms the falciform ligament, which connects the liver to the anterior abdominal wall.
The dorsal mesentery, however, has a much more complex fate, folding dramatically to form the fatty apron we know as the greater omentum.
That's the greater omentum. It forms from the dramatic elongation and fusion of the dorsal mesogastrium after the stomach rotates 90 degrees. That mesogastrium stretches, folds upon itself, and hangs down like a gigantic double-layered fatty apron over the intestines.
And the fate of the greater omentum is to fuse to other structures, essentially locking them in place.
Exactly. This four-layered structure eventually adheres and fuses with the mesentery of the transverse colon and adheres to the posterior parietal wall. This complex fusion dictates the relationship between the stomach, transverse colon, and posterior wall, limiting movement and defining boundaries.
This brings us to the most stable arrangement in the abdomen, retroperitonealization. Explain the specific mechanism that permanently fixes certain organs.
Retroperitonealization is the process where parts of the gut, which were initially suspended in the peritoneal cavity by a dorsal mesentery, are pushed against the posterior abdominal wall, as happened during stomach and midgut rotation. The dorsal mesentery then fuses completely with the posterior parietal peritoneum.
And then it disappears.
Over time, the fused mesentery is largely resorbed, leaving the organ fixed behind the peritoneum.
It's like gluing down the plumbing that must stay still, but leaving the coiling garden hose, the jejunum and ileum, free to move around for storage and flexibility. Which specific organs become permanently fixed by this glue?
The key organs that undergo this fixation, becoming secondary retroperitoneal, are the duodenum, except for its proximal segment, the entire pancreas, except the tip of the tail, and the ascending and descending colon. They lose their ability to move, which provides them with structural stability necessary for their roles as chemical processing and hydration centers.
We've saved a unique organ for last, the spleen. It is intimately involved in the rotation process, but is not actually a derivative of the gut tube itself.
The spleen is an anomaly in this system. It is not an endodermal derivative. It develops entirely within the tissue of the dorsal mesogastrium. It's purely mesodermal, arising from the focal proliferation of splanchnopleuric mesenchyme.
It's just a passive passenger on the stomach's rotational journey, but its location is entirely determined by that twist.
Exactly. When the stomach rotates 90 degrees clockwise, it pulls the dorsal mesogastrium to the left. The spleen, embedded in that tissue, is pulled into the left upper quadrant. This movement stretches the mesogastrium into the spleen's two supporting ligaments: the gastrosplenic ligament, connecting the spleen to the stomach, and the splenorenal ligament, connecting the spleen to the posterior wall and left kidney.
And fragments of that mesenchyme can sometimes persist, leading to a common finding.
Yes. Fragmentation of the splenic mesenchyme during this phase can result in small pieces persisting, known as accessory spleens, or splenonculi. They are often clinically insignificant, but highlight the mesodermal origin and the developmental plasticity of the area.
To wrap up the structure, we must discuss the specialized systems, the networks that control the whole factory, the nerves and the immune components. Starting with the second brain, the enteric nervous system, ENS.
The ENS is the intrinsic nervous system of the gut. It contains as many neurons as the spinal cord. It controls motility, secretion, and local blood flow. And the origin of the enteric neurons, which form the myenteric and submucosal plexuses, is distinct and absolutely crucial. They are derived from neural crest cells.
The famous neural crest cells, the migratory cells that form so much of the peripheral nervous system. Which part of the crest contributes to the gut?
Most of the gut's ENS is populated by neurons derived from the vagal neural crest cells, those that originate in the head and neck region. These cells must undertake a long, incredibly difficult migration down the entire length of the developing digestive tract.
And there's another source.
Yes, a small portion of the hindgut also receives input from sacral neural crest cells.
The migration process is the critical vulnerability here. If it stalls, the downstream consequence is severe.
The migration process is strictly craniocaudal, from head to tail. The cells must continuously colonize the tract, forming the myenteric plexus, which regulates motility, and the submucosal plexus, which regulates secretion and local flow. This entire colonization process is typically complete in the small intestine by week 12 and slightly later in the colon.
And the clinical link to the failure of this colonization.
Failure of this neural crest cell migration, often due to genetic factors or environmental influences, results in Hirschsprung's disease. This condition is defined by the absence of ganglion cells and a ganglionic segment most commonly found in the distal colon or rectum.
And in a ganglionic segment functionally means paralysis.
Exactly. Without intrinsic nerve cells, that segment of the bowel cannot relax or contract in an organized peristaltic wave. It is perpetually constricted, causing a functional obstruction that leads to severe constipation and megacolon proximal to the affected segment. This is a profound example of how a failure in cell migration during the 8th to 12th week of gestation defines a major chronic motility disorder for life.
Finally, let's talk about the defense system, the specialized immune tissue within the gut wall. When does the gut begin preparing for the outside world?
That is the gut-associated lymphoid tissue, GALT. This specialized immune architecture, which includes lymphoid aggregates like the well-known Peyer's patches in the ileum, makes a comparatively late appearance. These aggregates, which are essential for mucosal immunity, begin to form in the lamina propria around 14 to 16 weeks. This demonstrates that the sophisticated specialized immune structure of the gut is one of the final components to develop prenatally, preparing the system for its future interaction with the complex microbial world.
We started this deep dive with a simple endodermal tube and have finished by mapping a 9-meter-long, coiled, fixed, and highly specialized system. It's hard not to be truly overwhelmed by the complexity. The initial folding, the stomach's double rotation, the duodenum self-occlusion, the spectacular 270-degree midgut twist.
The fusion planes, the simultaneous growth of accessory organs, the migration of nerve cells.
All of this high-stakes choreography, driven by precise chemical signals like SH and PDX1, is executed over a matter of mere weeks. It's just incredible.
What's profoundly fascinating here is that the entirety of this microscopic developmental timeline is permanently written into the pathology and function of the adult body. The dual origin of the esophageal muscle dictates your voluntary swallow. The timing of recanalization defines the risk of duodenal atresia. The success of nerve cell migration determines diseases like Hirschsprung's.
And the mesenteries.
And crucially, the location of the mesenteries dictates where potential hernia sites occur. It is a powerful testament to the fact that adult anatomical form does not simply exist. It strictly follows its developmental history.
So what does this all mean for the body you inhabit right now? What's the final takeaway?
We must consider the ultimate and permanent consequence of that intense, controlled midgut rotation that happened between weeks 6 and 10. The establishment of the anatomical division of the entire abdomen into peritoneal, free-moving, and retroperitoneal fixed spaces.
Right.
The organs in the retroperitoneal space, the kidneys, the major vessels, the pancreas, the duodenum, parts of the colon, are fixed, immobile, and protected for life. And this permanent status is due to a mesentery layer fusing completely to the posterior body wall during that brief fetal rotation.
So here's the thought to leave you with.
How does the simple temporary fusion and resorption of a sheet of mesoderm, completed 8 to 10 weeks into development, define the lifelong stability and surgical accessibility of the major metabolic and excretory organs you rely on every single day? That temporary embryonic event is literally the immovable foundation of your permanent anatomy.